Hi everyone. This week we'll be covering chapter 2 of the book Primer of Medical Radiobiology by Travis. It's a really nice book. It's a little out of date, so we may deviate just a little, especially in the later chapters. But it's a really, really well written book. And if you choose to pick up a copy, then used copies can be found quite cheap. I think mine was like, I don't know, I think I got mine for like $20. Had a bit of writing in it, but it's fine. Chapter 2 of the book covers some basic physics of how radiation interacts with matter. So we'll be talking about that. We'll be talking about some of the definitions, so LET and RBE, and talking about some of the radiation effects on DNA, chromosomes, and I guess the cell in general. So let's get started and talk about the interactions of radiations with matter. So the first thing we need to recognize is that radiation is a very stochastic process, the interaction with radiation and matter. And that just means it's really random. So you can get uneven distribution of how the energy is deposited in the material. It's not just going to be sort of absorbed uniformly everywhere. Also, it happens very, very quickly. So, in terms of the, I guess, in terms of the actual, the actual photon or whatever interacting with a piece of material, we're talking like 10 to the minus 17 seconds fast, right? So it's incredibly fast. But we don't see the effects of this until after what's referred to as the latent period. And the latent period is just how long it takes for these effects to present themselves. And, this effectively means that, we're looking at changes in tissues or the organs, and they might not be seen until after weeks or in some instances, even years. Now, radiation is random. I know I just said that before, but it's important to emphasize that it isn't selective. So the radiation isn't targeting any particular area of the cell or the body or anything like that. However, we do talk about targets in this course, and we'll talk about targets a lot. But when we talk about targets, what we're referring to is susceptible sites. So this is basically areas of the body where if the radiation was to do damage, it would do more harm, right? It's more sensitive to that damage. But in principle, the radiation can do damage anywhere. There really isn't any preference in terms of where the energy is deposited. And it's not always unique, right? And what do we mean by that? Well, the damage caused by the radiation could be caused by other phenomena too. And so later on in the course, when we're, for example, talking about the correlation of radiation with cancer risk, well, many people get cancer without having been exposed to radiation. So it's not just a radiation effect. It could be caused by other things too. So ionizing radiation comes in different flavors. For example, we have alpha particles, which are helium nuclei with 2 protons and 2 neutrons. We have beta particles, which are basically energetic electrons, and gamma or X-rays, which are high energy photons. Now, all of these are ionizing radiation, and ionizing just means knocking an electron from an atom and converting that atom into an ion. But we can also excite an atom, and that means raising an electron from a lower energy level to a higher energy level. Photons can deposit the energy, as we've just described, or they can also scatter. And when they scatter, they can change direction, but with very little energy loss. Now, the reason why we refer to this as ionizing radiation is because it's the ability to ionize, it's the excess energy that is really kind of important about this type of radiation. One thing I want to talk about briefly before we move on is just the difference between X-rays and gamma rays. Um, so X-rays are produced by accelerating electrons into a heavy metal, typically tungsten, while gamma rays are emitted as the excess energy when an unstable radioactive nuclei decays on its path to becoming more stable. So they're both potentially the same frequency, the same energy, in all ways, essentially the same photon. It's all just how they're produced. All right, well, let's move on and talk about the photoelectric effect. Now, the photoelectric effect involves an incoming photon knocking an electron from an atom. If the electron is ejected from a more tightly bound orbit, then an electron from a higher orbit, a higher energy orbit, will then drop down to that lower energy orbit. And in doing so, the difference in energy between the higher and lower orbits will have to be released. Now, this gets released in what's called characteristic radiation. And the reason it's called characteristic radiation because it's characteristic of that atom. It's almost like a fingerprint that tells you what that atom is in a way. In soft tissue, this characteristic radiation has relatively low energy and probably isn't going to be of any biological consequence. It's not going to go on to damage the other atoms in any way. But the mass absorption coefficient for the photoelectric effect is proportional to the atomic mass, raised to the power 3. So basically, the more heavier the elements are, which in bone, contains heavier elements like calcium, the more this effect is gonna occur, and that's why heavier atoms in bone, for example, show up on X-rays. Moving on. I want to talk a little bit about Auger electrons. So when the characteristic radiation is being emitted, I say it's not of any biological consequence, but actually it could knock out an electron that's in a outer shell, so it's sort of a lower energy electron, and these are called Auger electrons. They are very low energy. So on the one hand, you might think, well, the low energy, are they really going to have that much of an effect? But the answer is yes. Yes, they do. They have it because they deposit the energy over very short distances. And we'll talk about this later. It's not just the energy that's being deposited, it's how it's deposited, right, over the spatial distances. So this is what's called high LET, and we'll define that term a little bit later. But basically, it can cause lethal damage to tissues, especially tumors, and so has a potential applications in radiotherapy. Moving on, there's also the Compton effect. The Compton effect is when a photon is scattered, deflecting it from its original path. However, the photon does lose some of its energy, and it does vary quite a lot. So it can lose anywhere from 0 to 80%. And where does that energy go? It goes to a loosely bound electron. Now, these electrons are so loosely bound, they're so outer, on the outer orbit of the atom, that in some ways they're almost free, right? And so when it's given that energy, it doesn't really need that much energy to escape from the atom. And so all that energy, or most of the energy, is given up as kinetic energy. And this effect, this Compton effect, it can dominate for high energy photons used for radiotherapy. For example, gamma rays produced from cobalt-60 that might be used to irradiate a patient. And these incoming photons then result in a large number of potentially fast electrons. And these electrons, they can do damage, but generally it's not the fast electrons that you got to worry about. It's when they slow down, because as they slow down, then they are more damaging. And we'll talk about that later in the course. The last effect is the Rayleigh effect. And this is basically just photon scattering. So they don't generally transfer any energy to the atom or to any electrons or anything else. It's just a change in direction of the photons. It's known as Rayleigh scattering. It does depend on frequency, and this is why the sky is blue. However, in terms of radiobiology, there isn't any energy deposited, so it really isn't of any consequence. The last sort of interaction that is worth sort of talking about is pair production, and it's kind of an interesting one. So basically, the photon comes in, and then there's a direct conversion from radiant energy to matter. So basically, you get a particle-antiparticle pair being created, most commonly an electron and a positron. And then in order to create this matter from basically thin air, the incoming photon has to have enough energy to do that. So this is E is equal to mc squared. So the energy is 1.022 mega electron volts. Now, to put this into perspective, medical X-rays are around 150 kilo electron volts, so much, much smaller than this. And if the electron positron recombine, so if they annihilate each other, then the two photons can be re-released, and you end up getting basically 2.51 mega electron volt photons being emitted. Just a really curious one there with the pair production. So just to sort of talk about then the interactions of the radiation and what essentially is going on, we have ionizations, which we've talked about, which is where an electron can be knocked out of an atom, and excitations, where an electron can be excited to a higher energy orbit. But the interaction can be direct in that it hits a target, right? And when we say target, we don't mean an area that the radiation is trying to hit. It's just that it's more susceptible to damage, or the cell's ability to survive or to propagate in a normal way is more susceptible to that damage. And then it can also be indirect. Now, indirect is the opposite, right? So indirect action is when the ionization comes in and interacts with other constituents in the cell. So it's not interacting with the target, which is the main part of the cell, typically the DNA, right? That is the most susceptible part of the cell. This is when the radiation comes in and hits, for example, the water. And when it hits the water, which accounts for 80% of the cell, it can create what's called free radicals. And those free radicals then can move around and diffuse around inside the cell and potentially damage those critical targets indirectly. Okay. Let's go through a quick example of this with water. So the ionizing radiation ionizes the water molecule. It basically takes an electron away from that water. And in doing so, it produces an ion radical. Now, an ion radical is both an ion, which means it's lost an electron or possibly gained an electron, and a free radical, which we'll talk about in a second. And of course, there's an electron produced as well. Now, these ion radicals are extremely short-lived, so they only generally survive on the order of 1 × 10⁻⁻10 seconds. But during that time, they can react with other water molecules. And if they do that, then they produce hydronium, which is H3O, and a hydroxyl radical, where the unpaired electron in the outer shell of the hydroxyl radical is represented by the big dot. And you may have seen this in chemistry, I'm not too sure. Now, what's the upshot of this? Well, a free radical is an atom, molecule, or ion that has at least one unpaired valence electron. Now, the unpaired electron makes these radicals highly chemically reactive, and they can cause damage to more targeted regions of the cell, right? Basically, the DNA. So, if these were to migrate or diffuse to where the DNA is, they could damage it. Um, Here's a little cartoon of showing how the free radicals are missing an electron from the outer shell, and they're all unstable, and so they go and steal an electron from another molecule, and then potentially damage that molecule and that cell, right? And antioxidants are unstable as well, but interestingly they combine with the free radical, and then they stabilize each other. And so you've probably heard of the health benefits of antioxidants, and this is the reason why, because they might actually sort of mitigate these effects a little bit. Now, regardless of whether it's a direct effect, right, a direct interaction of the radiation with the target, or whether it's indirect in terms of creating a free radical that then goes on to target the damage the target, the DNA. The ultimate result is the same. You have damage or alteration to the cell, right? In particular, the DNA. So let's sort of review the general sequence of events then that can occur for indirect action. So the X-ray comes in and creates fast electrons that can go on and cause more damage in the system. And ion radicals, right? Ion radicals are produced as well. Now those ion radicals combine with water molecules that can cause free radicals. And the example we went through isn't the only possibility for free radical production. That was just a nice, easy example we went through. But these free radicals then can sort of migrate to targeted areas of the cell and then cause, basically they can break the bonds that bind the DNA together, or other damage, and essentially cause chemical changes in the system, right? And we'll talk a little about that in a second. And then ultimately, after a latent period of days or even years or whatever, we might then observe some biological effects because of the damage done by the radiation. So indirect action involves the formation of free radicals. Direct action is when the DNA is damaged directly. Now, direct action dominates for more densely ionizing radiations, such as fast neutrons or alpha particles. Think of these particles like large bowling balls coming in and knocking everything out of their path. There is a dense line of ionizations along the path of the particle that is more likely to interact directly with the DNA. While there may also be lots of free radicals produced along the path with these heavier, more densely ionizing radiations, they do not add substantially to the severity of the damage because the direct actions are so much more prevalent. But if it's not dense, then the indirect can play more of a role. So a lot of this really comes down to how densely the energy is deposited.